Well, let me start by saying thanks to the organizers for putting together this program and, of course, for inviting me here. So I'm going to talk about Moire, phonons, and phasons. I will try to explain the difference and what I mean by that. The motivation is phenomenology of Moire systems, of course. Particularly, we discuss transport and superconductivity, and very briefly, a couple of new results or new effects regarding the optical manifestation of these phonons. So before we start, it's kind of cliche, but it's true. One of the best things of working on this problem for so many years now is having the chance to work with all these people. So this is a list of all the people that contribute to this talk, and I will try to mention all these names along the way. But in case I forget, there are two names that I cannot forget. One is the name of Alejandro Ramos Alonso, who's a student, a graduate student at Columbia University. Very smart student, despite the fact that he decided to work with me. Not the wisest decision professionally, but he's very good with physics. And of course, Rafael, with whom I've been working and discussing for years now. On this problem, it has been always a pleasure, and I learned a lot, and it was super helpful to understand many of the things I'm going to discuss. Okay, so before I enter into technicalities, let me give you an overview. So what do I mean by Moire phonons? So by Moire phonons, what I really mean is the collective mode that describes vibrations of the Moire superlattice as a whole. So the collective mode involving a lot of atoms within the Moire unit itself. And they come basically from relative motion, relative displacement, long wavelength displacements of the two layers of your twisted device. Okay, so they are dynamical heterostrain fields. Okay, so one way to think about the calculations is basically you can start from the acoustic phonons of single layer, and you can fold them back to the Moire Brillouin zone, and those are the dash lines. And now, because of this relative motion of the layers, that changes locally the stacking configuration, and together with a relaxation effect, etc., that basically reconstruct these phonon spectra. And you have now many flatter optical Moire phonons, and also a new acoustic branch, and those are the ones that I'm going to call phasons. Because basically they correspond, in the kind of continuum models I'm going to describe, to a phase fluctuation or phase shift of the solitone solution that describes a relaxation in the problem. So this kind of fluctuation that resembles like the acoustic phonon of the Moire superlattice. Okay? But generically it will be present in any incommensurate system. Okay? So the physical effect that I'm going to discuss in particular as pertain to this phason mode are related to the fact that despite that these are acoustic-like phonons of the Moire superlattice, they are very different compared to acoustic phonons because they always involve the motion of a group of ions with respect to the other. So that's the main observation. Okay? Now, as I said before, the motivation, of course, is the phenomenology of Moire systems. But let me mention this. Actually, I learned this from Rafael. So there are other systems, quasi-crystalline, that displays phenomenology that are, at least if we don't look very close, kind of similar to things that we observe in TBG, twisted bilayer graphene, and other twisted devices, which is namely, and this is the case of this compound of bismuth. So bismuth under pressure experience a sequence of structural transitions. Some are crystalline, some are not. Bismuth 3 is actually an incommensurate lattice. You can understand this as of these all incommensurate composite systems that people study in the 80s. Basically, you can think of a chain of atoms, of guest atoms that are in an incommensurate ratio with the host lattice. And this system, according to this report, is actually strong coupling superconductor with pretty large critical field that arises from a normal state, which has also this kind of strange metal behavior surviving down to very low temperature, this linearity surviving down to very low temperatures, but they always tend to saturate, which is similar to what happens in TBG actually. Okay? So what this system and Moire system have in common is that both are host for sliding phason modes. Okay? Okay, so let me give you a couple of slides with main results, and then the rest of the talk is just elaboration on this. So one of the results that we get recently is the fact that these phonons, the ones with appropriate symmetry, they are optically active both in Raman and infrared spectroscopy. Actually, infrared active modes, because the system is chiral, are also Raman active. For the Raman calculation, this is a calculation that Vitor Dantas, is a student of Natasha Perkins in Minnesota. They do this calculation. I'm not going to discuss much, but basically we have a kind of a macroscopic theory in which we understand how the polarizability of the bilayer changes. It's a function of stacking, and from that we can track the position and intensities of Raman peaks associated with the different modes. So if you're interested, have a look at the paper, or we can discuss offline. But I'm going to focus on this new result, which is unpublished. I'm like working with Alejandro on the manuscript these days. And it's pretty cool because it's this idea that, remember, this is coming from folding acoustic phonons in a system, a non-polar system like graphene. And yet, when you dope the system, the phonons couple directly to light. Why? It's because an effect that we have been discussing for a couple of days now is because now the charge that you add in respect to neutrality is inhomogeneous in the Moire unit cell. So all the Moire phonons with appropriate symmetry, actually, they are gonna borrow spectral wave from the electron hole continuum and form a dipole moment that couples directly to light. Including, and the optimal situation to observe that is a situation in which you put 4 electrons per Moire, so you have the front bands fill, and you have here the electron hole continuum, so these peaks corresponding to these interband transitions. And now some of the Moire phonons are going to appear as resonances within the optical gap of the system, including the phason mode. And this is not difficult to understand. Actually, this is a very nice geometrical interpretation I will explain, but this is not different than the sliding conductivity of a charge density wave. Okay? So that's one thing. The other is related to this problem on which we have been working for now years, and is, again, the idea that the problem of scattering of electrons by phasons is very different compared to the problem of scattering with acoustic phonons. And the reason is that, because as I said, we always have group of ions sliding in respect to the other, and therefore this kind of motion is always subjected to friction. What that means is that the response, the mechanical response involving this kind of motion of the system is dominated for modes that are propagating for short wavelengths, but diffusive in the long wavelength limit. So these phasons become overdamped because they are not true Goldstone mode like an acoustic phonon. The linear momentum of relative linear momentum of 2 layers is not of conserved quantity. So that has consequences on the temperature scales of the scattering problems involving transport and also now superconductivity. And we have new results that I think we're about to publish, and these are calculations involving Ellis-Beer equations for a model that I will describe at the end of the talk, done by Banuildo Silva de Carvalho. So let me walk you through this diagram. So this is temperature, the vertical axis, and this is a phenomenical parameter that basically represents phason lifetime, which is finite at 0 momenta. When this is 0, so this axis corresponds to the typical acoustic phonon problem. And then you have linear interior resistivity down to block donation temperature, and then higher power. This is the block donation regime, and eventually you can become a superconductor. Now, and the problem with phasons, now in order to build this diffusive peak, this diffusive response, basically you have to transfer a spectral wave of these bosons from high to low energies. And the consequence of that is that now simple equipartition now can survive down to a new temperature scale that is lower than block donation temperature. And then at the lowest temperature, resistivity is always T squared. It's Fermi liquid-like. And this happens when transport is dominated by small transfer phasons with a small transfer of momenta, which are always overdamped. So this is what we call incoherent regime. And an interesting observation, based on the solution of these Ellis-Beer equations that Banuildo did, is that depending on the strength of the electron-phason coupling, when you study a theory of phason-mediated superconductivity, you can have either superconductor arising from a Fermi liquid-like looking metal or strange metal-looking metal. Okay? Yeah. It's gonna add, unless it's somehow aligned, and maybe there are some kind of commensuration effect, and maybe it's gonna pin and therefore kill this phason mode that is not gonna be so low energy. I will say it will add to this damping constant. No? I will say so, yeah, I will say so. Yeah. It's it's a true Goldstone in which context? If you are in a continuum theory, I agree with you. This is truly a Goldstone mode. But so where is this coming microscopically? This is the same as question. I mean, can you calculate microscopically tribological properties of this bilayer system, etc.? Of course, but these are super hard. I mean, these are macroscopic dissipative. It's coming from friction associated with the fact that you have rugosities and harmonic coupling also to these flexural modes. It's like riding a bike with low pressure in your wheels, right? So, for example, the fact that the thing can oscillate out of plane, that also can increment friction. But also in a model, you have to start from a atomistic model. Then you kill, okay, so then I should correct my answer, and maybe in that case, which is encapsulated, if friction is mostly coming from the fact that you are sliding and doing this, maybe in that case, friction actually is lower. That's a good point, yeah. I don't know, so I'm not going to discuss microscopic origin of this parameter. This is a phenomenological parameter in the models, and I'm not going to try to impose a point of view about phenomenology. I'm just trying to point out like possibilities coming from a different perspective than most people, coming from ideas in soft matter physics, because this is kind of a soft matter system too. So that's what, yeah. You can put bounds. Yeah. You can put bounds, and maybe you can, yeah. So you can put bounds because you can actually, a lot of people studying tribological properties of these super lubric graphitic systems. So they have some estimates for the phonon lifetimes in this system, etc. You can learn from that community. That's what I was trying to. I didn't get much, but yeah, you can put bounds on that also from microscopics. But I prefer not to discuss that because I mean I'm changing opinion all the time from one week to another depending on which paper I read. So it's like a. Okay, so those were like the highlights. This is the outline. So first I'm going to spend some time discussing models, and I will describe this idea of staking order and how we do the phonon calculations, just to introduce some language. Then I will do an application in twisted TMDs. I believe nobody discussed twisted TMDs so far. Probably tomorrow we'll have more talks. But actually it's interesting because in the case of twisted TMDs, because they are polar, you can actually control the phonon dispersion with electric fields. Which is pretty cool. And then I will discuss a minimal model of the coupling of these Moire phonons and phasons with electrons. And I will I will discuss this calculation of the optical conductivity that I mentioned at the very beginning. And I will probably spend most of my time discussing the electron phason scattering problem. Okay, please, yeah, I welcome questions anytime. Okay, so how we model the system. So I like to talk in terms of this stacking field. So this is an object, which is a vector object that is going to appear in most of the equations I'm going to show. It's just a way to parameterize different stacking configurations. The idea is that you start from perfect overlap of the two, in this case, graphene layers, so AA stacking. And by sliding one layer respect to the other, you can generate all kinds of stackings, right? So this is a way to parameterize stacking. Important observation is that in this configuration space, there's some sort of redundancy, because if I just slide one ray with respect to the other, and a vector corresponding to a Bravais vector of this commensurate system, then I end up in the same configuration. So that is going to impose some constraints on the formula. And the idea is that now I have a lattice mismatch, for example, a reed rotation, which is what I'm describing here. And now that introduces a spatial modulation on this stacking field. So now the stacking is a stacking field that must be understood as a relative displacement field of the layers, but it's better to think of this displacement field in Eulerian coordinates. So I'm not going to do Lagrangian elasticity. So no lambda Lipschitz elasticity. Cherenkov-Lubensky elasticity. And I will always assume, and that's why we're going to use continuum models, that the spatial modulation of this field is smooth on the atomic scale. And that is true for a small twist angle, even when you include lattice relaxation. And the reason is because this is a 2D material problem. So very stiff within the plane and very soft out of plane. Okay, so the calculation of the phonons comes basically in 2 steps. So I'm going to write my now dynamical field in 2 pieces. This is what I'm going to call the ground state, subjected to some boundary conditions that basically fix the twist angle. And what I need to do is to minimize some free energy functional. And the free energy functional, I didn't write the equations here, but they are very simple. This is basically a term that describes the elasticity of the 2 graphene layers, plus an addition potential or stacking potential that depends on this stacking, local stacking configurations, right? And because of this redundancy in the description of configurations in stacking, necessarily this potential has to be periodic with the periodicity of the original graphene lattice, okay? So basically, for twisted bilayer graphene, it's a very simple parameterization with a single parameter that I'm going to call V at some point that describes the free energy difference between AA and AB addition energies, okay? So you minimize this, so basically you have to solve the nonlinear saddle point equations describing adhesive forces equals stress. And then you expand in fluctuations, you stop at harmonic order, and then basically you compute this object, which is, because and this is an important point, because this periodicity in configuration space, once you introduce a boundary condition, in this case the twist, is always going to be manifested in some spatial modulation with some periodicity. In this case, the boundary condition is the twist angle that imposes the periodicity of the Moire period. So everything is going to be translational invariant in the Moire superlattice. So basically, this object, this dynamical matrix, is a very big matrix spanned by the Cartesian indices of this vector and Moire reciprocal lattice vectors. Okay, so you compute these derivatives, you build a very big matrix for each momenta restricted to the Moire-Johnson, and you diagonalize, and you have the polarization of these modes on the energies. So this is how typical calculations look like. Actually, this is an actual calculation for TBG. This is how we impose the boundary conditions. So we write the equilibrium configuration as a stacking configuration produced by a reed rotation, and that's kept constant, plus some displacement, and this is the one that we determine self-consistently by solving this saddle point equation. So basically the idea is that this introduces, because of the periodicity in configuration space, some periodicity in Moire lattice. So think of this density plot as the landscape in real space of addition energies. There is a lot of energy cost associated with these big AA stack regions. So what the system does in order to minimize energy is to amplify the twist angle in some regions and to expand the regions of partial Bernal stacking, AB, B stacking, which are the minimal energy configuration. So when you combine the two, what you have is this Moire, which is sharper now in the Moire scale, and you can think of this as a network of domain walls separating, similar to the ones we discussed this morning, separating regions of Bernal stacking and connecting these AA stack regions, okay? So now there are two length scales in the problem, the Moire period, and now from the competition between the two terms in the free energy, we have this length scale, which is the width of the domain wall, okay? This is V, and this is the shear modulus, because most of the strain contained in these solitons is shear strain because of the twist. Okay, so now as promised, I'm going to discuss TMDs. And as I said before, TMDs are interesting because they're non-synchronous, they are polar. And what happens when you twist is basically you are exploring different high symmetry configuration, including this XM, MX stacking configuration. So this is chalcogen on metal and metal on chalcogen. And these are connected by mirror reflection. And what happens is that you have some charge transfer there, and you have a dipole moment forming in these stack areas, and the opposite one in the other. So you have a polarization texture within the Moire cell, an alternating polarization texture. And now, if you apply a vertical electric field, you couple to this polarization, and basically you favor energetically some commensurate areas with respect to others. And this is what you can see here in this STEM image, in which you can see gray and black areas are the two different stacking configurations, and sometimes you can have kind of a hysteretic response. This is what is called sliding ferroelectricity. So there are papers by Pablo Jari Herrero and Mose Ben Salom on this stuff. So the idea now, I'm not going to show equations, just simply the idea now is that we have now a new interaction term with this vertical electric field, and that introduces a new length scale in the problem, which can be seen as the competition between the linear tension of these domain walls, can be thought as strings under tension, divided by the difference in addition energies between now the twin equivalent stacking configuration. And this corresponds to the bending radius of the domain wall. So you're going to see that in the calculation. So we have left panel. Left panel is stuff similar to twisted bilayer graphene, so zero electric field. You have the domain walls forming. As you decrease the twist angle, this becomes sharper and sharper on the Moire scale. And you see here the evolution of the Moire phonons. An observation is at the beginning, for example, for the phasons, the sound velocity gets a little bit smaller, but actually it converges pretty quickly to like a constant value. What happens now, here I'm focusing on the case of 1 degree. What happens now if for this system we apply an electric field? So you can see the deformation, right, the bending of the domain walls, right, that increase the area of one stacking with respect to the other. This is similar to the TEM image that I saw before. And that increases to the point that now they are so bent that actually these domain walls meet in a new misfit dislocation, and actually the topology of the lattice changes completely from a triangular lattice to a honeycomb-like soliton lattice. And the effect on the Moire phonons is pretty remarkable, because now with electric field, the phonon changes dramatically, and in particular what happens is that many flat bands of phonons appear here. This can be understood as standing waves of these domain walls subjected to new boundary conditions imposed on this honeycomb lattice. And very importantly, one of the phason modes, the longitudinal phason mode, which is the lowest energy, becomes super soft. Why is that? Let me keep that. Let me just skip that. The reason is because, and that's another difference between this kind of incommensurate lattice and a true crystalline lattice. In a crystalline lattice, we think in terms of springs. Energetics depend quadratically on the distance between ions. In these incommensurate lattices, these are strings under tension, so energy scales linearly with the length of the domain wall. And that changes completely the game. That's the reason why the longitudinal phason has lower energy than the transverse phason, contrary to what you will expect for acoustic phonons. And also, there's something remarkable about these honeycomb soliton networks, which is sort of a topological property of this lattice, which is the fact that you can distort the areas of the hexagon, but as is very well explained in Chinky-Lubensky, keeping the perimeter of the hexagon constant. So if you keep the perimeter, the length constant, necessarily that means that it's going to be a zero mode in the phonon spectrum. And this is the reason why we have a softening of this longitudinal phase. Okay. Let me move on. Let's discuss now. Let's move from TMDs back to twisted bilayer graphene again. Let me discuss minimal continuum model to describe electron phonon and electron phazon coupling. So this is how we think of the continuum model of the Sitzer-McDonald model in real space. So we have this kind of KP expansion. These are like field operators around the valleys, the two original valleys. And this object is just a 4x4 matrix. These blocks are just Dirac Hamiltonians for the top and bottom layer. You can add here terms, like the pseudo gauge field, deformation potential, etc., depending on symmetrized derivatives of this field. So basically heterostrain, that is contained there. And you have also interlayer tunneling events described by this matrix. So basically this describes electrons tunneling from one layer to the other as the superposition of three plane waves coming from the three equivalent Dirac points of graphene to preserve C3 rotation. Okay. So this looks pretty much like the model we are all accustomed to. The only difference now is that the phase that electrons grab when they tunnel now is modulated in space by this stacking field. And the idea is that, okay, this is super minimal theory, local, not including all terms that are relevant, that break electron-hole symmetry, and they're typically amplified by relaxation. Very minimal model, but the idea is that now we have this Hamiltonian. I can expand to linear order in the stacking fluctuation. I have now a Hamiltonian that, if I have relaxation effects in this field, describes some relaxation effects in my bands. And of course, the first linear coupling with the phonons. And this fluctuation contains now all the phonons. So that's the idea. Of course, if here you evaluate the stacking field corresponding to a rigid rotation, these equations correspond to the Sitzer-McDonald model. You can just check that. Okay. And now what we are going to present, just to introduce notation, is the only thing I'm going to do in that theory is to introduce a new basis of normal mode coordinates for my phonons after I diagonalize the phonon problem, and of course fermion operators after I diagonalize the electron problem, and the matrix elements of the electron phonon coupling can be just computed from derivatives of the Sitzer-McDonald Hamiltonian, or its, you know, a straightforward like continuation with respect to these normal mode coordinates. Okay, and in principle we could learn these numbers from experiments thanks to the quantum twisting microscope. Important thing is that these numbers do not correspond to these numbers. My understanding that these numbers are matrix elements of the electron phazon coupling between two plane waves of the bottom and top layer. These are matrix elements in now the diagonal basis that diagonalize the Sitzer-McDonald Hamiltonian, not the same thing. Okay, so let me show you the optical conductivity calculation I was referring to. So this vertex is a vertex with phonons. This is a phonon propagator. This vertex is the vertex with light. So it's a current operator. So you have basically your typical current response function defining first contribution to the conductivity. This is the electron hole continuum. And now the first contribution from the collective mode that is given by this diagram. And this can be written as this combination of response function. These bubbles are response function missing currents and stacking configurations in these normal mode coordinates. And this is just a phonon propagator. These are the energies of your phonon. This rho is the mass density corresponding to the relative inertia of this kind of motion. That's why there is a 2 appearing here. So it is the mass density of single layer graphene. And this gamma is just my phenomenological damping parameter, which is going to be finite for all these modes. And this is the result of the calculation when you neglect for simplicity relaxation effects. So you play with the original Sitzer-McDonald model. Okay? And as I said, it's like via these mechanisms, you can check from the causal structure of all these components that basically this conductivity satisfies F-sum rule. So basically these guys borrow F-sum rule spectral weight from the electron hole continuum. Numerically, 98% comes from this range of frequencies just to build these resonances. And that's basically it. No? So dipolar fluctuations of the Moire, when you add charge into the Moire, they couple to light. And you can see that in with some kind of sterile spectroscopy. Let me discuss the, yeah. So this situation in which so the flat bands are fully occupied, okay? So you have the gap. These are these two transitions basically, and you have a bunch of Moire phonons with belonging to the E1 representation that lie at energies corresponding that are within the gap. So you can see those. Typically, there is always an overlap, and then sometimes you see like a phano-like shape. And yes, we are like trying to do all the calculations. You can dress this propagator in RPA. There is not much effect. So typically relaxation effects like have a stronger impact. But yeah. Let's discuss. So let me discuss the phason, which is like this tiny thing. Who cares, no? But conceptually, I do. So the idea is the following. Why I'm identifying this acoustic phonon with a phason is because if I go to the zero momentum limit, the kind of stacking fluctuation that this phason produces should correspond to the kind of distortion of the equilibrium stacking configuration that comes from just like shifting the coordinates, okay? Which means that in principle I can always make a change of variables from normal modes in stacking fields to this coordinate that I'm gonna just call the phason coordinate. And now, for example, this eta is just a dimensionless numerical factor when there is no relaxation, meaning that basically the phason corresponds to a rigid translation of one layer respect to the other. That number is 1. And what this equation describes is just when you translate one layer respect to the other, the Moire flows in the perpendicular direction. A quantity that is amplified by the twist angle, the inverse of the twist angle. Now, when there is relaxation, now your phason is a coherent superposition of optical modes. It's something more complicated. Still, you can make this change of variables, but now this coefficient describes how much of the sliding of this domain wall corresponds to a real rotation, and how much is really rearrangement of the atoms in this sliding motion of the domain wall. So basically, now, and that enters in the definition. So we check this numerically. That is always true. Basically because all these components of translations with a capital G that appears here actually are always proportional to the first derivative of the stacking field. You don't need to do actually a calculation. You can just by arguments. So instead of stacking fields, it's convenient to do the calculation in these phason fields. And now, if you go to the limit of zero frequencies, these bubbles that I saw before have a very clear meaning. So basically, the result that you get is, of course, our phason propagator. And now these bubbles can be expressed in terms of this coefficient C, which is just the integral of some mathematical object that corresponds just to the Berry curvature that you can define in a mixed space of momenta and phason shifts. So the Hamiltonian is modulo unitary rotation, periodic both in quasi-momentum and phase translations. Okay, and this is how this looks like for the McDonald model when you put 4 electrons per mass. It's mostly concentrated at the gamma point. And when you integrate this and some over occupied bands with care, actually this guy times the area of the Moire cell is actually quantized by the number of electrons that you have added per Moire cell. And the argument is very simple. It's simply that when I'm sliding one layer with respect to the other, the Moire is flowing, and if I'm doing this very slowly, the charge that is located in the AA stack regions is going to follow adiabatically the flow of the Moire pattern. Okay? Is this pumping effect that Di Xiao, Mikito Cosino, and others discuss. And in this paper that nobody paid attention to, I discussed the reciprocal effect, because on Sager reciprocity means that if this is true, now an electric field has to produce a shear mechanical force between layers. And that's the meaning of the other. So I'm done with time? 5 minutes, okay. So I'm gonna run, but basically when you end up from these arguments is that basically the phason is like dragging this chart that we are adding, and you end up with some Drude-like formula for the phason peak, in which you can basically identify the effective mass now of a charged Moire pattern, okay? So let me move on very quickly, because I only have 5 minutes, to this problem. So motivation is the strange metal behavior, and I'm gonna use, I typically make this point that the resistivity, regardless of temperature dependence, always saturates, of course, because we start populating the dispersive bands. But that's just making a point that this metal is strange, but it's not a bad metal like the cuprates. Okay, so phenomenologically, it's maybe something different. And really, this is just a way to justify what we do, which is Boltzmann transport theory. Okay, so these are the typical equations for Boltzmann equation and resistivity, and everything that is relevant is contained actually in this scattering kernel. When you can have here, you see here now the phason fluctuation described by this propagator. Now, so let me discuss this very briefly, and then I will move on to superconductivity, and then I will finish. So imagine I simplify the model. So now I have just a circular Fermi surface coupled to longitudinal phason fluctuations through electron density, right? Through gradients of this field. So this is like a deformation potential coupling. So the coupling is just like the one that you would expect for acoustic phonon. Okay? And of course we have this temperature scale, Lagrangian scale, defined by the maximum momentum transfer with the Fermi surface. So above this scale we expect linear anti-resistivity because of equipartition theory. And the problem for any phonon-based theory is that this number is large, because the the graphene is super stiff, so the sound velocities are very large. Okay. Now, what happens now in this problem, in which now we incorporate a finite gamma in the propagator. Now we have a new temperature scale defined by this gamma, and now we have two different regimes. When T gamma is smaller than Broglie-Nassen, that means that most of the phasons scattering electrons are actually just propagating waves. So basically, nothing changes much. But in the opposite regime, all these modes are diffusive. And if you analyze all the integrals involved in this calculation, now things depend not on these two scales separately, but actually in this scale, this temperature scale that you can form with these two temperature scale. And this is the new T star. So now resistivity is linear in temperature down to this new scale that is nominally lower than the Broglie-Nassen scale. So that's the argument. You can do lot of calculations in this actually toy model that I show. It's like you can do like analytical estimates. And we did numerics to understand data at samples, minimally twisted samples of 0.4 degrees. And the theory works pretty well. This is phason, this is phonon contribution to resistivity, phason wins. Dependence with density is okay, these are experimental data. And very important thing in these experiments is linear in T over across 4 minibands. And then to the lowest temperature is always T squared, which is also something that the phason theory predicts, but not the, this is not what you would expect for acoustic phones. And that's my last slide. So superconductivity. We studied basically in this toy model that I discussed, phason-mediated superconductivity, and we solve Elias-Verr equations. And when I say we, it's really Vanildo. Elias-Verr equations for this model, assuming just S-wave pairing. And these are the results. Critical temperature is always, or gamma, finite gamma is always detrimental for critical temperature, contrary to some claims in the literature. And actually, just from the BCS limit of the equations, you can actually get these analytical results that actually describe very well the scaling of TC with T gamma in this diffusive regime, and also dependence on the dimensionless coupling, which is essentially linear. It's the same scaling as T star, and depending on how large is lambda, you can have this transition from a strange metal to a superconductor, or from this incoherent T square resistivity to a superconductor. So that's basically the message, and I just summarized all the messages in these 3 bullet points. And happy to take questions now.
Okay. Yeah. Thanks a lot for the talk. So one question is, so for in twisted biographene, one thing is that the resistivity is a function of temperature, is linear. The other thing is that the slope is extremely high, right? The slope is something like 500 Kelvin. Is this something that one can also get from the model?
Sure, because the good thing about the model is that you just put the numbers there and then it works. No, so of course the model is not quantitative because it's a phenometric model. So you have to be careful. So I'm not going to make a quantitative. You cannot make quantitative guess based on this simple. So that's why I restrict the discussion to the temperature scales. It's very surprising, this huge slope with temperature.
Right.
Now, if you compare data in this minimally twisted graphene, again, our calculation is not quantitative. We try, but it's like it's not working. And something I think I didn't mention, and is relevant to your question, is that for this sample, resistivity is linear in T. It's much larger than resistivity in single layer graphene, but way smaller than linear in T resistivity at the magic angle. It's somewhere in between.
Right. Yeah. So basically, if you look at 2 degrees, for example, twisted bilagraphene, also the slope just is quenched. So you definitely get the high temperature linear dependence, but the slope is like completely quenched.
Which could be that phasons, for example, are contributing to the linearity, and they are always present. But they are not enough to explain data at the magic angle. Something else is happening at magic angle. That's perfectly possible. Yeah.
Okay. All right. Thanks.
Thank you.
Yeah. No, this is not part of the story. No, I wouldn't say so. I don't know. What do you think? It's all Fermi liquid. Yeah.
This lambda is not the lambda you're saying.
There's the lambda that you're thinking, right? It's actually, I think I didn't write the definition, but it's the coupling with acoustic mode, so maybe that's the reason why. It's different.
The one that was export.
Right.
Yeah. Yeah, sorry for the confusion.
And so and for the density dependence, you said there is some density dependence to the linearity there.
Sorry, let me go the other direction. Yeah, right. So is this one? So this is data at this temperature. This is our calculation for phasons. Not in this toy model, but actually we try like a solution.
So it's up to half filling, right? Or
no, this is filling. So this is full. Right. This is up to half filling of the first flat band. Yes.
Right. And so it disappears kind of at charge neutrality, and then it peaks.
Yeah, it peaks around the Lipschitz transition, the Van Hoff.
I see. Okay.
And here it's very difficult to do calculations, so we didn't try. But more or less follows the trend.
So the Bloch-Grüneisen temperature disappears at 0, or?
Sorry?
The Bloch-Grüneisen temperature disappears at 0, or?
We didn't try neutrality because always, right. I mean, Boltzmann theory breaks down there, so you cannot extend this to.
The strongest linearity should be at around 0, right? Then in this picture.
Here we are subtracting. This is only phonon contribution, right? So it's like the data we are in this data actually we are subtracting the disorder contribution, the extrapolation of data to T0. So that's that, and that gives you the peak.
So let me press you a little bit on the quantitative side.
Okay.
Right?
Okay.
So if I plug in some numbers that make sense. So normally I agree with you that the BG temperature is put in the literature is 10 to 30 Kelvin, but actually if you look at the coupling of a linear boson, the linearity starts much lower than TBG. It starts at the TBG over 10. True. And if you take into account the normalization of the phason, that's another factor of 2, so that you can get down to around 1 Kelvin, even for the simplest no frills theory. Of course, it doesn't explain the 50 millikelvin that
Yes.
sees, but you can get down pretty much. How much lower can you go with realistic parameters?
Okay, so I have here, so I have this estimate. I typically just show this and I don't explain where I'm coming from. This is your 1 Kelvin. And this agrees if I take gamma, which is the phase-on lifetime that people typically use in simulation of traveloidal properties. Those are in superlubric conditions, meaning that there is essentially no relaxation effects or disorder. Now, imagine that it's very disordered system, which is bad news for our phase-on study, but nevertheless. What is the other energy scale that I can invoke? Is just, which is a small number, it's just the adhesion energetics of this I mean, it's like, yeah, that's the typical order of magnitudes of interactions between layers, because all this is coming from interactions between layers. You just take that number, then I have the 50 millikelvin. So realistically, somewhere in between, probably closer to 1, if I'm honest.
And this is at what density?
I'm not considering here electron density. This is just coming from spectral properties of the phason, only invoking mechanics. Now, your point is that if I charge the system, now electrons contribute to phason damping. Maybe this is a calculation or an estimate you can try to make and see how that depends on filling. That's an interesting calculation. Yeah.
There is one very important issue that we've been struggling with, which is that once you have a phase B, you can couple V with tau. And that is going to, instead of the gradient that you couple the acoustic element, and that certainly is going to affect. But we still, I mean, it's not an easy problem. And
Sure.
we talked about it.
Sure, it's not.
Yeah.
Tricky, but you were right that I agree completely that electrons away from Turner project, because the Turner project perhaps there's a gap and we don't need to worry about it. But then the whole thing is meaningless. They will probably do so.
I think.
And then just to add that, the way that we found where the scenes can start talking to each other to break the symmetry that is artificial to continue is also via this phase of flexor.
The flexural modes,
And
which
then,
goes to.
it's another can of worms that I would be happy to discuss.
No, that's a complicated problem.
Okay, thank you.
Okay, if there are no more questions, then let's thank the speaker one more time.